So today it's our great pleasure to welcome Steen Hannestad, and I'm completely mangling his name and his affiliation because my Danish is not very good. He's professor at the University of Arnhem,
You're getting there.
And so also, like, under his many things, the things I wanted to point out, that he's a guest scientist at CERN as well as the Max Planck of Physics in Munich, and he will tell us about cosmology and how neutrinos are a great laboratory. Changed title a little bit, but basically how neutrinos are a great laboratory to check out cosmology.
Okay, thanks a lot for the invitation. Yes, so what I wanted to tell you about for the next 45 minutes is, I think, one of the nicer connections between cosmology and particle physics. Of course, we know that cosmology and particle physics are connected, especially through the very early universe. So you have very high energy physics, presumably being responsible for phenomena like inflation, for example. So what I'll talk about is much more mundane. It's very down to earth particle physics that you would typically go out and try to test in a direct experiments somewhere here on Earth. Except neutrinos are notoriously difficult to measure, and therefore in certain cases cosmology is actually a competitive lab for doing neutrino physics. And that's something I think it's really nice. Of course, in the future we hope that the same might be true for the physics of dark matter, for example, and that neutrino cosmology is only in a sense a prototype for how to do this. So let's just briefly go through all the sources of neutrinos that we have around in the universe. Many of them are astrophysical. Historically, the first place where neutrinos were detected were in reactors, and that is actually coming back now as an important source of neutrinos for doing precision experiments. Other than that, for a long time we've had accelerator-based neutrinos, both short baseline experiments where we can measure neutrino fluxes, long baseline experiments where precision tests can be made of neutrino oscillation properties. Then we have a nice source of neutrinos coming from the upper atmosphere. We have high energy cosmic rays hitting the atmosphere, producing pions. These pions in turn decay and produce lots of neutrinos that can be measured in neutrino detectors. We even have low energy neutrinos coming from below, so there are lots of radioactive stuff in the mantle of the Earth that decays and produces low energy neutrinos that can actually be measured. It was first detected in 2005 and has now been measured at great significance. The Sun, of course, is a copious source of neutrinos. About 10 billion neutrinos hitting each square centimeter of the Earth every second. We know that supernovae produce enormous amounts of neutrinos. In fact, the luminosity in a typical type 2 supernova is comparable to the visible luminosity within a Hubble volume while it lasts in neutrinos. And then we have an important new lab, in a sense, for doing neutrino physics. I'm not going to talk about that today, but it's very interesting. So this year we had presumably what is the first detection of high energy neutrinos coming from astrophysical sources. So from sources that are not, well, the atmosphere or the Sun, but somewhere else in the universe. So that was detected by the ice cube experiment on the Antarctic. What I wanted to talk about today is this final piece in the puzzle, namely the Big Bang neutrinos. The neutrinos that are known to be around us in the universe, about 100 per neutrino flavor per cubic centimeter everywhere in the universe, roughly. We know they're there. I'll tell you why. We know that they've been detected at way more than 5 sigma significance. So we know the neutrinos are there, but we cannot measure them directly. Even though we can see them only indirectly, we can still learn quite a lot about them. Yeah, that was one of them. So you can see them from time to time. Okay. So what else do we know about neutrinos? Well, first of course, they are very different from other fermions of the Standard Model. So all particles, all fermions of the Standard Model have mass, as far as we know. They all have masses that are perhaps slightly below what you would naively expect for particles having new color couplings to the Higgs, but that's not very extreme. But for neutrinos, the effect is really very extreme. So something is odd about neutrinos. They're very much lighter than other particles in the Standard Model, electron volts or below. they don't have electric charge. Maybe these two things are connected somehow. In fact, they might very well be connected. So in any case, there are plenty of strange things about neutrinos. So what do we want to know? Well, it's basically the same type of question that you'd want to ask for other particles in the Standard Model, except here we don't really know the answers yet. So we want to know what is the mass hierarchy. So we know there are three flavors of neutrinos at least. We don't know the mass ordering, and we don't know any of the masses. What we do know are the mass differences here. So between these three flavors of neutrinos. Those can be measured from neutrino oscillation experiments. It's one piece of the puzzle that's actually known. And we also know what is called the mixing angle between neutrinos. I'll show you in a little while exactly what I mean by that. We don't know the absolute value of the neutrino mass. It can't be anything, but we don't know what the exact value is. There are various ways of getting at this quantity. I'll get to that in a minute. We can measure it, or hope to measure it either directly via tritium decay, for example, or we can measure it indirectly using cosmology. Then there are some more fundamental questions that are actually extremely interesting. So, for example, neutrinos are the only particles that we know of, the only fermions that have no electric charge. That means they can actually be their own antiparticles. They can be what is known as Majorana particles. So that's very different from the other fermions in the Standard Model that have charge. We know that the antiparticle, of course, has opposite charge, so it cannot be identical to the particle. That can be the case for neutrinos, and in fact it might very well be the case for neutrinos. There might also be more than 3 neutrino flavors around. In fact, there's some tentative evidence from various sources that additional neutrinos might be out there waiting to be discovered. So that, of course, would be extremely interesting evidence for physics beyond the Standard Model, if it turns out to be true. So first, these first 2 points, the mass hierarchy and the mixing angles. So what we do know about neutrinos is that they can change their properties. So once a neutrino is produced in a charge current interaction, so it's produced as a particular flavor of neutrino, electron, muon, or tau, then it propagates, then you go out and detect it, and it might not be the same thing anymore. Because when it propagates as an eigenstate of energy and momentum. If those eigenstates are not the same as the eigenstates of the electroweak interaction, then you can actually change the property of the neutrino as it propagates. So that's a phenomenon known as neutrino oscillations. It's observed in nature in great detail. And you can also describe how the flavor eigenstates here are related to the mass states here. And you have this nasty big mixing matrix, and you have lots of elements that you need to measure. For example, these rotation angles, so they correspond to the Euler angles in usual three-dimensional rotations. Then there are complex phases that have to do with CP violation. And so the good message here is that for the rest of the talk, I won't really care very much about this. You can measure it in various ways. But the point is that the type of cosmology that I'll talk about here is really insensitive to the flavor structure of neutrinos. All we care about is very simple. We care about energy density. And energy density, that's parameterized in terms of the mass states only. So we don't care about what type of flavor a neutrino is. That makes life a lot simpler. So that means that if we want to describe, say we have neutrinos floating around the universe, we want to describe how much energy density is in the soup of neutrinos, then we need to know the masses. So we know the mass splittings from these oscillation experiments. We know there's one traditionally called the solar mass splitting here that was historically first seen in solar neutrino oscillations or in solar neutrino experiments. And then we have another one called the atmospheric mass difference that was historically first seen in atmospheric neutrino experiments. Both of these have been confirmed by other experiments, reactor experiments in this case, and long baseline neutrino oscillation experiments in the other case. So we have an established sequence of neutrino masses. And it also means, of course, that only one neutrino can be strictly massless. So at least 2 of them are known to be massive. What we don't know is the ordering. So for example, you can shift the hierarchy here. So you can make the blue one, the third mass, you can make that lighter than the other 2. That would be opposite of all the other fermions happenings in the standard model, but it's not experimentally excluded at this stage. We know the sign here, because when neutrinos propagate out of the sun, they propagate through what's known as a matter potential. They feel the background of whatever is in the sun, and what is in the sun is mainly, in this context, electrons, not positrons. And because the sun is highly CP asymmetric, it only contains electrons, not positrons, that fixes this hierarchy here. So we do know a little bit, but we don't know the normalization here. That's the problem. So you can shift the scale up or down, and there's no way that any oscillation experiment can ever tell you about this, because it only measures the mass differences. So in order to get to the absolute value of the neutrino mass, you have to do something else. So either you try to measure it directly from tritium decay, I'll show you that in a second, or you find some other probe of neutrino mass, and in this case, cosmology is what I'll be talking about. Okay, let's just skip that. So the other direct way of measuring neutrino mass, that was, like I said, tritium decay. So what you could measure is, you have some element, in this case tritium, decaying, you have an outgoing electron, you measure the energy spectrum of that electron, and then you look for effects close to the end point here. So if the neutrino was strictly massless, then the electron can take away all the energy. If the neutrino contains mass, then it can't take away all the energy. You have to keep at least the rest mass of the neutrino, and you can see the difference here. And you can try looking for it. The problem, of course, is that you're looking for a tiny, tiny, tiny effect where you have almost no electrons. So it's a really, really difficult measurement, and there are lots of systematics going into it. So this is the present state of the art. This is from the Mainz neutrino mass experiment. It's actually quite a few years old by now. So they were able to set an upper limit on the effective electron neutrino mass, and now I already made a point that, of course, there's no such thing as an electron neutrino mass, because the electron neutrino is not a mass eigenstate, and therefore it doesn't have a specific mass. So it's really a combination of the mass states here. If you put all of this together, you'll find that the total neutrino mass should be less than about 7 electron volts or so. So just to give you an idea about what will happen in this field in the coming years, well, this is the historical record going towards ever-increasing accuracy. In some cases, actually finding weird results. So for example, for a long time, the favorite neutrino mass from these directed detection experiments was negative, which is kind of worrying, of course. This is caused by systematic effects, of course. When you have an electron propagating out of whatever medium you have the tritium in, it can lose energy, and that can lead to, you have to correct for that, and then you can get spurious effects like negative masses, for example. Or, of course, you can believe in crazy beyond the standard model physics. That's the alternative. Now, in the not too distant future, we will do much better, hopefully at least. We don't know that yet, but at least we have a very good candidate for taking us down about an order of magnitude. That's the Katrin experiment, the Karlsruhe tritium neutrino experiment, that is almost ready to go. An old picture, I guess many of you have seen this already, of course, in the media or in talks. You see the main spectrometer of the Katrin experiment being transported to Forschungszentrum Karlsruhe. You also perhaps can see from this why it's hard to upscale an experiment like this. The sensitivity to neutrino mass goes as the square root of the diameter of this thing, basically. And the point is you have to guide the electrons adiabatically from the source to the detector, and in order to do that you have to have a large spectrometer in order for, well, to maintain adiabaticity. So for example, this should be able to do about 0.2 electron volts. If you wanted to go down an order of magnitude, then you'd be looking at something which is not 10 meters diameter, but, well, a kilometer diameter or so, 2 orders of magnitude bigger. So that's not feasible, evidently. Actually, as a strange aside, in Denmark we are also familiar with this type of experiment. We have these large beer fermentation tanks that were brought to Carlsberg, so they have an uncanny likeness with the technology. Might be coincidental. Okay, so let's skip forward and get back to the more serious business. Why is it that cosmology can even measure the neutrino mass? Well, the point is that neutrinos are known to be there is just pure, simple, low-energy standard model physics, perturbative and everything. It's just weak interaction physics, basically, plus linear perturbation theory in GR. So what you have is a calculation of when neutrinos decouple in the early universe. Of course, they interact weakly. That means that they cannot keep interacting throughout the lifetime of the universe. They actually decouple when the universe had a temperature of about 2 MeV, or an age of a little bit less than 1 second. Based on that calculation, we know what the number density of neutrinos is in the universe. Now it's about 100 per flavor or per mass eigenstate per cubic centimeter. If you then know the mass, it's very easy to calculate what's the contribution of neutrinos to the omega parameter, so to the cosmic density parameter. And you get a relation which looks roughly like this. So if the sum of neutrino masses was of order 10 electron volts, then this would be of order 0.1, and neutrinos would be all the dark matter in the universe. So historically, neutrinos were the favored dark matter candidate, except they have extremely wrong properties for a dark matter candidate. They have this nasty feature that they freeze screen. Okay, they're low mass particles. They go non-relativistic very late in the evolution of the universe, and that means that if you have initial perturbations in the density, then neutrinos will erase them on a scale up to what is known as the free screening scale of neutrinos, which is basically just the distance a neutrino can cover before it goes non-relativistic. And that's a large distance. So for a 1 eV neutrino, you're looking at a distance of about a gigaparsec. So any perturbation on scales less than a gigaparsec would be erased. And that's evidently something that would have been observed. So I can show you 2 simulations. Hopefully it might work. Yeah. Okay, so one simulation is just standard lambda CDM. The other one is with dark matter replaced by neutrinos. So what you can see is that there's almost no structure in the simulation here. So they're based on the same set of initial conditions. But the problem here is that only the very largest scales survive. So for example, anything like a galaxy would have been impossible to form in a scenario where neutrinos were all the dark matter. So clearly that means that the neutrino mass cannot be anywhere close to the bound from the Mainz experiment. It cannot be anywhere close to 7 electron volts for the sum of neutrino masses. It must be much smaller than that in order for structure formation to proceed. The question is, how much smaller should it be? So in order to get to a number, of course, we just need to look at all the data that we have available. So we have the CMB temperature map that's excruciatingly precisely measured. It's really quite astounding. The problem is that this is not particularly sensitive to neutrino mass. The reason why the CMB is not in itself very sensitive to neutrino mass is that neutrinos are relativistic particles at the time where the CMB forms. So imagine you have a neutrino of 0.2 electron volt mass. That has a mass comparable to the temperature where you have recombination. But that means that it's essentially a relativistic particle when the CMB is formed. So it doesn't know about the neutrino mass. In fact, the main effect of neutrino mass on the CMB spectrum is from gravitational lensing of the signal propagating from the recombination surface down to us. What is very sensitive to neutrino mass is something like this. So the large-scale distribution of galaxies, I already showed you this simulation before, where you can really see that all the small-scale structure is erased. And that's well, not a very perturbative effect, it's a really important effect. So if you look at something like the large-scale structure matter power spectrum here, and you look at what the effect of a neutrino is, you get to something like this. This should have been, well, it's converted from Windows to Mac, so weirdnesses might occur from time to time. Okay, so the benchmark here, this is just standard lambda CDM. Then you start increasing the neutrino mass. You see for a sum of neutrino masses of 1 electron volt, you're looking at a 50% reduction of structure on small scales. So it's certainly a visible effect, even with present data. And even if the neutrino mass was really, really small, the smallest possible value it could have would be the mass differences measured in oscillation experiments, right? So you put one mass at strictly 0, and then you add up the other 2 masses. and then you find about 0.06 electron volts. So that's the smallest possible value you could have. In that case, you still have several percent effect, which might be visible, not with present data, but with future data. Okay, so then you take your set of data, you crank your Cosmo MC wheels or whatever other algorithm you're using, and out comes a number, of course. You have some constraint on the neutrino mass. Hundreds of papers in the literature exist, all quoting some number. This is from the PLANCK publications. So here, for example, with PLANCK data only, they claim a bound of about 1 electron volt for the sum of neutrino masses. If you add auxiliary data like varying acoustic oscillation, so essentially the data that I showed you before, that was the matter power spectrum, not the BAO data itself, but it's pretty much the same thing. Then you get down to about 0.3 electron volts or so. So of course, this could just be taken to be the number. The problem is that, as always in cosmology, things are not that simple, right? You're doing some likelihood analysis of a big parameter space. You have to constrain a lot of parameters simultaneously. You have to make choices about the data sets you're using. So you can all put it in a matrix like this. You can start from the simplest model that is known to fit the data. Then you can put the neutrino mass on top of that, and then you can make a constraint. That will tend to give you a very stringent bound. Then as you increase the model complexity, of course you loosen the bound because you have more freedom. So a large neutrino mass could be compensated by other parameters. And eventually, if you're optimistic enough, you can even make the bound go away pretty much. Then you start adding data sets of, increasingly less robust data sets, let's put it like that. So for example, if you stick to this type of model and you pile data sets up, then eventually you might get a detection. It might not be a real detection, it could very well be a spurious detection of a neutrino mass, so it might not be very believable. Or if you try to stick to this side here and be super conservative, then of course nothing will ever happen, and others will beat you to it. So you have to use some kind of common sense here. So this is just to warn you that there's no single number I could possibly give you that is the answer to what is the current bound on the neutrino mass. It's somewhere in the range below 1 electron volt, but that's pretty much as far as you can get at present. Okay, so just going one step further, the neutrino mass, that's a pure standard model thing, but of course you might also test physics beyond the standard model in a neutrino context. So one possible place of doing that is to test, okay, what is actually the amount of energy density floating around out there in neutrinos. We know the standard model prediction for it, but it's also a value that should be measured because, of course, it might not come out as the same value as the predicted value. Okay, so the prediction in crazy units here is exactly that you have 3.046 neutrinos, types of neutrinos. That's of course a nonsensical result because we know there are 3 flavors, so the number should be 3.00 and not 3.046. The problem is that we're normalizing this to a strange number, this one here, defined relative to the photon density. And this makes certain assumptions about neutrino physics around the time of decoupling that doesn't hold exactly. So there's small corrections. There are also finite temperature corrections that you need to take into account. So the canonical value is this one. And then you go out and measure it in the same way that you would measure any other cosmological parameter. You look for a data set that is sensitive to this parameter. It might, for example, in this case, be the CMB. You come up with some bound for this number. And historically, even going back to the Stone Age, the time before WMAP, where I was also one of the authors on some of these papers here, so I also date back to that era. The bound wasn't particularly impressive, but then as the data has improved in quality, of course the bound has sharpened. And there was always this preference for a value that was slightly higher than 3 at a level where it might be incompatible with the standard model prediction, although not at very high significance. So everyone longed for the Planck data to settle this question once and for all. And the problem, as always, with converting stuff from Windows to Mac, is that stuff disappears. So there should have been numbers here, and not in black. Well, okay, you can read the conclusion here. If you take the PLANCK data, then you might massage the data in such a way that it looks as if the problem has all gone away, but then once you start scratching a little bit beneath the surface, you find that the problem is still there. You still prefer a value that is slightly higher than 3, but not at very high significance. So it's not like a 5 sigma detection of physics beyond the standard model. It's again back to something like a 2 sigma detection of something. So we don't unfortunately know what the result is at the moment. And yeah, okay, so this is one of the versions that actually comes out not black. So you can see that depending on the data set that you're combining, you might find a value that is completely compatible with 3, or you might find something that is higher than 3 at some significance. This might have something to do with the measurements of the Hubble parameter. So you might know, of course, that there's a discrepancy between the directly measured value of the Hubble parameter, which is above 70, and the Planck inferred value of the Hubble parameter, which is 67. There might be a number of reasons for that. One reason might be that non-standard neutrino physics is around that can actually reconcile the two numbers and both would come out compatible. So that's one possibility. Or there might be something systematically in the current Planck data set that is not accounted for, that of course is not known, but might be the case. Okay, let's skip through this. Okay, so let's entertain the possibility for a moment. I'm not saying this is actually true, but let's just entertain the possibility. Then neutrinos might be the source of this extra energy density. So there might just be more energy density in neutrinos than we think. This could be either because every single species of neutrino is more abundant than we think, or it might be because there are other neutrinos out there that we don't know of. So you could call this, for example, sterile neutrinos. Sterile neutrinos just means that they don't have standard model interactions. They can still be produced in the early universe, and they would be out there and they would contribute to the cosmic energy density and therefore be measurable in the CMB, for example. So that's a possibility. It's actually something that is entirely compatible, and you can show that it's compatible with current observations. It's actually also hinted at in neutrino experiments. And if I was a salesperson, then I would say that well, there's strong indications that sterile neutrinos are around because there are a number of separate hints all pointing in the same direction. But of course I should also warn you that in neutrino physics, historically, this was always the case. There are always anomalies in neutrino physics. And to go from the anomalies that are seen today to infer that sterile neutrinos, that additional sterile neutrinos are around, that would be overdoing it, in my opinion. So there might be some evidence that additional neutrinos are around. Of course, it would be spectacular if they are detected, but I wouldn't, I think, bet any real money on it. Okay, but at least what you can show is that sterile neutrinos are, to some extent, compatible both with short baseline oscillation experiments and with cosmology, provided that some additional stuff is put in. The problem is that from short baseline experiments, these are the green contours, those are ones that include the neutrino oscillation experiments. You always come out with a value for the mass of the neutrino which is around 1 electron volt. That's a bit high for comfort for cosmology. And what happens is that you can also constrain the energy density in these sterile neutrinos. And 1.0, that would be exactly one extra neutrino species. That is not really very favored. You would always tend to prefer neutrinos that are not completely thermalized. Unfortunately, that's not, well, the canonical prediction. If you have these sterile neutrinos, the normal prediction would be that they are completely thermalized in the early universe. You have to come up with some new physics in addition to them being there in order to prevent them being produced in too large an amount. That you can do. Of course, there are always ways out of these things. So this was just one possibility. The bottom line in this case is just that sterile neutrinos are very much alive. It's not that they are excluded by cosmology. They might be there. And I should also say that it's still true that extra relativistic energy density is actually one of the most likely places for beyond standard model physics to show up in cosmology. So it's really something to look out for in the future. And that brings me to the last part of my talk, namely what is actually in store for the future. So you've seen now that cosmology can do pretty good things for neutrino physics, but we're not quite there yet. There are no firm detections of anything. So that, of course, is where we want to get. And the question is that, will that be possible? Well, we will have nodes of better data. So in the coming years, there will, for example, be very large-scale measurements of weak gravitational lensing. So the idea in this type of measurement is this, that you have some plane of sources here. They could be any type of light-emitting objects. They could be high-redshift galaxies, for example, or it could be the CMB emitting surface sitting out here at large distance. Then you propagate the signal through this inhomogeneous universe, and you will get a distortion of the original image. So imagine that you started from this idealized case where you have only spherical sources. Then you propagate it through an inhomogeneous universe, and gravitational lensing will distort the image such that every single object becomes elliptical. So for example, if these are galaxies, you're in trouble, right? Because galaxies are intrinsically elliptical anyway. So how do you distinguish this effect from the intrinsic ellipticity? And the answer is that the gravitational lensing phenomenon is coherent over large scales. We just average over many galaxies. And then, well, the intrinsic part will go to zero. It's not exactly true, but it will almost go to zero. And then you're left with the weak lensing measurement. So that is a known technique. It's been used for many years to measure the masses of galaxy clusters, for example. So that certainly works. The new thing is that this can be scaled up to measure what corresponds to the large-scale matter power spectrum, but now measuring directly the gravitational potential. So that's a new technique. And you can quantify it in terms of a power spectrum, and then you can, again, crank your wheels of your Boltzmann code, and you can convert it to a power spectrum, and you get something like this. So this is a typical weak lensing power spectrum. The neat thing here is not so much the spectrum itself, because it looks kind of bleak and featureless compared to a CMB spectrum, but the point is that you get to choose the redshift of your light-emitting object. So unlike the CMB, where you have one emitting surface, you could now have high redshift galaxies or low redshift galaxies. You can look for lensing distortions in both of these separately. So for example, this could be a high redshift sample, this could be a low redshift sample. You see that the high redshift galaxies are more lensed, of course, because light propagates through more of the inhomogeneous universe. You see the shape is not the same, so you have time evolution of the lensing signal. And the conclusion is you can do actual tomography of how structure forms in the universe by this technique. So that's very powerful. We also actually have experiments that are doing this, experiments that will do it in the future. So currently running experiments like, for example, the PAN-STARRS experiment, the Dark Energy Survey, which is just starting up now. In the slightly more distant future, there will be the Large Synoptic Survey Telescope, and then there were always historically these space-based experiments that everyone agreed would be the ultimate in this field. None of them ever materialized, but that situation has changed. So we now have the Euclid satellite, which is a funded mission. 2019, of course, will presumably be way too optimistic with regards to launch date, but it will happen, that's the point. And it will do spectacular things. It will measure essentially half of the entire sky out to large redshift, so we're talking about a substantial fraction of the entire Hubble volume being measured. So it will do weak lensing and photometric galaxy measurements out to large redshift. It will also do a spectroscopic survey doing baryon acoustic oscillations, and there will be an additional cluster survey. So this is all really nice. And just to give you an idea, if you look at the current Sloan survey compared to the entire Hubble volume up to redshift of 1100, then Euclid will do something like this. So it's actually a quite substantial fraction of the Hubble volume. That gives you loads of Fourier modes in terms of a power spectrum, for example. So you really have a lot of statistical power in this. And it can do interesting things for dark energy. What I'm mainly interested in is what it can do for neutrino physics. Actually, if you go back a few years, people in this field were hardly interested in neutrinos at all because they were presumably massless particles just floating around and you needn't care about them. The problem is that we're now getting to a precision where not accounting for a massive neutrino will seriously bias your dark energy measurements. So for example, you could be led to believe that dark energy has crazy properties if you don't take neutrinos into account. So actually this has led the community to start worrying about neutrinos. That's kind of nice. So we did a forecast last year just to get an idea about what you can do with Euclid. And impressively, if you don't think there are any showstoppers in terms of systematics, you will actually have something like a 5 sigma detection of the neutrinos based on the Euclid data. That's quite neat, I think. You can also measure this effective number of neutrino species, now parameterized in a slightly crazy way. So 2.046 is now the standard model value. That's not the important point. The important point is that you're getting to a precision with Euclid where you can actually measure the difference between 3.046 and 3.0. So you can actually go out and measure finite temperature QED effects in the early universe using something like this. That's quite impressive, I think. So of course there are also, well, not so pretty things that you have to worry about, because in order to really get to that precision, you have to be able to calculate from first principles the, for example, lensing power spectrum to 1% precision. That's highly non-trivial and not something that we really want to get into, but unfortunately we have to do this. So we have to worry about baryonic physics, we have to worry about neutrinos, all kinds of things. So we did a lot of simulations of neutrinos and structure formation, and there are actually significant effects of nonlinearity that you have to account for through large n-body simulations. It can be done. The good thing about neutrinos is you can actually do it. And you can get pretty pictures out of it. That's nice, of course, as well. And I think time is up. So this is just to show you where we're heading in the coming years. I think it's certainly true that neutrino physics is perhaps the best example of how you connect particle physics with cosmology, because it's all very down to earth. We're not talking about Planck scale physics or anything like that. And you're actually super competitive with cosmology in terms of what you can measure. There might be hints of beyond standard model physics, so there are interesting things lurking out there. And with Euclid, many of these questions will presumably be answered. Okay, so let me stop here. That's an excellent question. The problem with the KV sterile neutrino, now you're talking about the warm dark matter candidate. The problem with the KV sterile neutrino is that it has to have an extremely small mixing angle. If it had a large mixing angle, it wouldn't be thermalized in the early universe, and we wouldn't be here because there would be only sterile neutrinos in the universe. So it has to have a very small mixing angle. That means that you're looking at very, very, very small effects. So for example, if you're looking at the flux of neutrinos being suppressed due to the mixing, then you're probably somewhere in the range of a 10 to the minus 8 effect. That's just not possible with present precision. The Catherine experiment has also looked into this question, and I think the honest answer is that it's really a long shot. It's unlikely to be possible. The EV sterile neutrinos, that will be a settled issue using short baseline oscillation experiments in the not too distant future.
Do you have any other questions? Okay, let me just ask one bit. You showed this really interesting simulations where you said that how many different modes actually use completely different evolution of the streamlines.
Yes.
And so I was wondering, what are the error bars on those lines? Like, can you do a first approximation of 10% is the new
The nice one and the not so nice one. Okay, the green lines, they are calculated in linear perturbation theory. So within the context of linear perturbation theory, there's essentially no error bars. I mean, that's less than the thickness of the line. So everything is extremely well controlled. The problem is that as the universe evolves, these scales actually become influenced by nonlinear gravitational evolution. So then the question is, how large is the error bar on this line rather than the green one? And that is more substantial, but it's nowhere close to, say, the distance here. It's basically within the scatter here. So the error bars from baryonic physics, of course, are substantially larger. The neutrino physics part can be controlled relatively well.
I have a very naive question. So we talked about ET, stereo neutrinos, KD, stereo neutrinos, which is one factor. So could it be, because your argument in the beginning was neutrinos cannot be a model for a cold dark matter because they are too good physical essentially.
Yes.
So what about this crazy idea? Maybe there are insanely massive neutrinos somewhere in model, and they are so massive that they're immediately cold when you produce them.
Yeah. Okay. So that of course is again it's a nice possibility when you first think about it. One of the problems with having very massive neutrinos is that they're actually unstable. So at loop, of course, you can still have the neutrino being stable, but at loop level, for example, you will always have a radiative decay of this neutrino. That's almost impossible to avoid. There are certain models where you can do it, but it's not very natural. So the problem actually with the KV star and neutrino is that you would start to see them. If you make them cold enough that they conform to the bounds that we have on warm dark matter, they become so massive that they will start to radiate in X-rays. And you would actually see X-ray radiation coming from galaxy clusters, for example, apart from, of course, the usual X-ray emission. If you make them even heavier, it becomes a lot worse because this goes as mass to the fifth. So it becomes really nasty, and it becomes, of course, much more like a line radiation. The higher the masses, the smaller effects you have from other quantities. So that's the short answer. It's extremely difficult to have a very massive neutrino, but nevertheless, of course, the massive neutrino is kind of the prototype for the WIMP particle. It's a weakly interacting massive particle. You just have to stabilize it. So that's what's nice about the lightest supersymmetric particle, for example. So you impose a new symmetry that stabilizes it. But it has all the same properties as a heavy neutrino would have.
Could you say something about the baryonic physics limitations? I thought that you just need to have some test particles. You need to know anything about their property. They could be round, oblong, whatever.
Yeah, it would be nice. It would be extremely nice if that were true. The problem with putting variance into these simulations is that you have lots of, you can have phenomena like shockwaves propagating, for example. So baryons are strongly interacting particles. They are not just gravitationally interacting test particles. So you actually have outflows of gas, you have supernovae going off. So you're talking about, for example, with the supernova physics on very small length scales, eventually influencing very large scales. So that's a really nasty problem from a simulation point of view. So of course lots of work goes into this, and much more work than goes into simulating neutrinos, because that's comparatively easy. But that's far from a settled issue. And I would not be telling the truth if I said that you can control the calculation of the large-scale matter power spectrum to 1%. So these baryonic effects are substantially larger than 1%. If you go to large scales, then it's not such a big problem. But that's not going to be enough for Euclid, for example. So there's lots of work that needs to be done here.
What constraints do we actually have in the couplings of the surrounding neutrino?
That's an extremely good question. We have a paper out on that tomorrow. It depends on what you mean. If you talk about couplings to standard model particles, they must be extremely small. They would be so small that they are unimportant. What we cannot possibly constrain, or which is very difficult to constrain, is how strongly self-coupled, for example, the sterile neutrinos are. So they can do all kinds of crazy things as long as they keep it secret from us, as long as they only self-interact. It's very relatively easy to constrain sterile neutrino interactions with us, so anything with the standard model, basically.
So the background of why I'm asking is because I'm wondering how would they thermalize?
How would what?
How would they thermalize?
Ah, okay, the thermalization, yes. So that's a very nice phenomenon. That's actually because what is sterile is the flavor state, not the mass state. So if you have mixing, then of course you have one additional mass state which is then substantially heavier. And that additional mass state, that is mainly sterile, but it can easily contain some small admixture of the active flavor. So every time you kick in a neutrino, there's a certain possibility that it goes into the sterile state. So if you just start from an active neutrino plasma, you will actually start to thermalize these sterile neutrinos just through the mixing and the interaction of the active neutrino. So as soon as you have mixing, something like this will occur. So that's qualitatively the easiest way of thermalizing a sterile neutrino. Then of course you can imagine all kinds of crazy things like they have Planck scale couplings, you have some heavy particle that can decay into sterile neutrinos. But you don't need something as esoteric as that. If you want sterile neutrinos that are related to the anomalies that you see in experimental neutrino physics, then indeed they do have to have mixing, because otherwise you wouldn't see them. And once they have mixing, they thermalize in the universe.
Can I ask a follow-up question? Then would you expect an effect of that mixing on the exploding mechanisms of supernova?
Yes, presumably you would. So some people have looked into this. So there are papers by Joe Spuller, for example, in his group, and there is an effect, yes. It's not known exactly quantitatively what the effect is, but there's sure to be an effect. And for sure it also has an effect on the type of neutrino spectrum that you would expect to be seeing from a supernova. Yes. So it's an obvious place to look for it, that's for sure.
Are there some other questions?
I have another question about the EV sterile neutrino. So you can't get neutrino masses from that, right? So for example, something like the seesaw mechanism or something like that, you need much heavier sterile neutrino.
No, you need a much heavier right-handed mass. So that, I mean, of course you can always think that maybe one of the right-handed neutrinos is EV mass, and then you have several much more massive right-handed neutrinos. So there are certain scenarios where you can do something like this, but the EV mass neutrino doesn't do it by itself, no.
I have another question. In the beginning you were saying that there are some indications that we have neutrinos with different flavors, or kind of different ones coming out.
Yes.
A, to speculate, and B, to would that actually influence the stream status of masses that we're talking about?
Well, the additional flavors would be presumably something like the sterile neutrino I talked about, because there is this bound from the decay of the set from lab saying that light neutrinos, and light meaning lighter than 45 TeV, coupling to the set, there are exactly 3 of those. You cannot have any other flavor of neutrinos. So if you have more neutrinos, they have to be sterile in some sense. They cannot couple to the set.
Would that actually make any difference in propagation?
Well, the sterile neutrinos, of course, behave somewhat differently, but from a structure formation point of view, from the point of view of what I'm talking about here, you can't distinguish a sterile neutrino from an active neutrino, because both are non-interacting. They're just gravitationally interacting particles. They're so weakly interacting that it doesn't really matter.
So the change in mass will also not change that cosmological structure?
Well, the change in mass, of course, makes them very different. But you can't say if you have a 1 electron volt active neutrino, that behaves exactly like a 1 electron volt sterile neutrino from a structure formation point of view. You can't really tell the difference between them.
Any other questions?
in the last bullet of your last page.
Yes.
You said that future instruments
Yes.
may give a positive detection of a non-zero
Yes.
mark. But that would then not be the first one, first such detection, because we already know these differences from the other.
Yes, for sure. Yes. Of course, it's not true that, okay, I should have phrased it slightly differently. It's absolutely true that it's not the first detection of neutrino mass in the sense that we do know mass differences. It's the first detection of the actual physical contribution of the neutrino mass to something. The oscillation experiments only measure mass differences, right? So they only measure, phase shifts essentially of the propagating wave functions.
And assuming you raise things like negative mass, the something will be zero. Yeah, okay, I got it.
In principle.